Hello, we're gonna talk about interference of waves in a very. We're also gonna look at a couple of assumptions we'll make when we do this calculation. So maybe some assumptions. Uh, we're gonna talk about the assumptions also. All right. So, what is this thing called interference of waves? Uh, so first, uh, what happens is when you have two waves come in, and in some region here, some space here, say screen, and say this is two light sources. It can be wave, can be sound wave, microwave. So they have two sources of light, and they kind of spread out, you know, and somewhere here they overlap. They overlap. Then under certain conditions, I'm going to talk about conditions in a minute. So under certain conditions, and you're going to hear the word coherent sources. Okay. So under certain conditions, you will see that the intensity kind of varies over here. So some places, it's almost like a beat. As you walk down here in space, you're seeing beats. You see intensity high here, high here, high here, high here, and then you see no intensity over or low intensity here, low intensity here, low intensity here. So a thing which causes this is called interference. It's said to be as a result of interference. Interference of there are two sources, 1 and 2. Interference of waves 1 and 2. So this is a physical thing. You've probably seen this in a in experiment. You've probably done this so-called Young's double slit experiment. Double slit experiment. It turns out this is a very definitive proof. If you see something like this, then this is a very clear proof that 1 and 2 are these guys that are coming together over there. They're waves. This can happen in waves. So if suppose this was a bullet, suppose you had a bullet, if you're shooting bullets in there and they came together over here, then these guys will not give interference. No interference. So if you have something to particles, a classical particle, so this is a classical particle, then you are not going to see interference. What you see in case of bullets, if they were coming together, you are going to just see kind of blob. You're not going to say, so the bullets just show like, suppose you're target practicing it or something, it's that kind of stuff you'll see. But you're saying two people are shooting bullets in a similar region and they're kind of overlapping, then they're trying to shoot the same place. Here, two waves kind of want to shoot. Want to shoot this high peak area. Okay, so they're the center of these two, and then still you see the other peaks. Here you just see one peak. So we say that interference experiments kind of reveal if something is a wave or not. Okay. So if I want to do it, let me do some kind of proof or calculation what to expect. So we will say our calculation, we take two simple waves, and see what we can what should we expect from calculation. So this will be like a theoretical thing showing that this is possible, right? This emerges from, if I take a wave over here and a wave over here, can I see the pattern emerge mathematically? All right, so we need to set some things up as to do it. Do a calculation. Say this is some kind of z-axis, and maybe we'll screen straight. Okay, we were here. I had to go do something. So we're looking at two simple waves we want to study and bring them together, and the word bring together and see if what I see a pattern. So we'll take a point source of a wave and another point source of same type of wave. It's light, so some point source of light, another point source of light. If you say water wave, it's some ripple here, some ripple here. And if you want sound wave, this some speaker, this some other speaker, and things like that, right? So and ideally it will be more like a spherical wave that starts out here, and I'll go very far away, and over here I'm going to look at when the two waves come in, what happens over there. So it's going to be hard to draw. Oh, I missed it, and so I want to take it, this other one. Oh, there's another hard to draw on this surface. Okay, so I've got these two waves. They come in over here at some point P. So you can say, if I'm looking at the x-axis, say, so at some point P, there's going to be, it will have some coordinate that I will know, and then I want to know at different values of this x, what will I see over here. So if I can figure out a rule of I want to have intensity here, intensity as a function of x, right? So if I know from the experiment, if these were coherent sources, what should I expect? So to be simple, let's see, we would do what is called scalar approximation. So simple for us will be, I made a big deal about waves being electromagnetic waves being polarized, and we'll just say scalar waves, meaning just not a vector. So I know electric field is, if it's this way, then magnetic field is that way. In electromagnetic waves, and k will be in the direction it's going, right? Over here, this wave is to meet at P is going in k1 direction, and this one over here in order to meet k2 direction, and you can see they're not the same. So you'll if you were to make it more complicated, you would say, hey, this even plane polarized electric field will be this way, only that guy emitting over there, and this one is even more tilted. So they're not the same direction. But we are going to not want to deal with this complication, so we can just say scalar wave. Forget about this vector nature. You can, if you like, you do this full-blown vector calculation. With this scalar calculation, you get 95% of physics already. So you get most of the physics already. I just cooked it up, this number 95, I don't know what percentage, but very high percentage, most of the physics. If you say don't like the numbers, stay like a politician, you can say, hey, most of the physics I get it, without telling you what the most means. All right. So we get most of the physics, and we don't worry about this extra complication that come from using as a vector. So that's one simplification we're going to do. We're going to do more simplification assumptions just in a minute. We will also assume that this wave and this wave start out in sync. What do I mean by in sync? Well, if this was say a source, so this wave is going out, say, like this, then this guy is also going out like this. So they start out in sync. So that's a in sync assumption. So that's assumption number 2. Number 10, for simplification, now not assumption but simplification, I'm going to do, they have this wavelength lambda is the same in both of them. So there's one lambda, one frequency. So assumption number 3, same frequency. Turns out to be extremely important. If they are different frequency, they can only vary so much from each other, and you're going to lose the effect here. So this is a important. Okay, same frequency. All right. So how do I write these waves? So I'm going to write wave 1. Let's call it E1. I still call it electric field, but let's call it E1. E1 is going to, when it reaches at point P, what does it look like? So E1 at P is going to be some magnitude E01, and hello cosine, but if it's a K1 and it's got the K1 magnitude, same wavelength, right? So for same wavelengths, so K1 equals to K2, that's 2 pi over lambda. We're going to call all this K. So it's if it's going in this direction, then let's call this distance R1. This distance R1. So we know inside here you have a K dot R minus omega t, and there is a phase constant here, but I'm not going to worry about that for simplification reasons. So this will be K times R1 minus omega t for the first wave. For the second wave, I'm going to get at point P, we're looking at what happens when they get over there. E02, you might say, hey, you know what, why don't you just say that this is same as that guy? They're the same number, whatever the amplitude is. That we can do that too also, but let's just keep it a little bit different. Turns out this doesn't cause too much trouble for us in calculation. So this distance will be R2. So k times r2 minus omega t. All right. So far so good. Yeah, you all fine with that? Uh, so what we have now is at p I have two waves coming, and so you're gonna have sum of the two. At p there's gonna be only one electric field, which are gonna be all the waves. If I have more than two, I'll add them all, right? So I just have two of them. Then you're gonna get this, right? Let's I have running out of time, so I'm just gonna do same amplitude, so it's kind of much easier to work with. So you've seen something like this when you add two cosines. Remember the beat phenomena we did? It's gonna be exactly same kind of this. So it's gonna be cosine A plus cosine B, right? That's formula. A for this, A for that, and B for that. Then I get 2 times E0, their difference and their summation, right? So cosine k r1 minus r2 over 2. So I get this part. Omega t, I took the same omega, so they cancel out just nicely, right? Nice. And then I have add them, divide by 2. So I get a k r1 plus r2 over 2 minus omega t. Add them, divide by 2 is the same. So I have actually at p electric field is actually an oscillation. So these things are fixed, right? So r's are known. So at p this is some value. So this is some amplitude at p, and this is kind of a oscillation. It's kind of a cosine delta, maybe let's call it theta minus omega t. So this is some number, constant number. So this is oscillation, just oscillation, right? So it's not a wave. It looks like a wave kind of formula, but it's not, because this is just some number. This can be R1 is fixed, R2 is fixed because I've fixed P. So all of these are some number. So this amplitude at P, and this oscillation, you can see that is going. So if you were to multiply, if I were to plot this at E at P with time, so it's going to be just oscillating cosine. Right? So, and this amplitude is AP, so whatever the value is, so it goes between minus AP and AP, and it just oscillates back and forth. It's kind of a simple harmonic oscillator. So this is just same as simple harmonic oscillator. This is same thing. The whole course is over simple harmonic oscillator, right? Well, how much is energy in it? Because we want intensity. So intensity is actually, if you look up the formula for intensity we have derived before, we are going to get some constant. So there's some number here. It's some say alpha, some constant, and we have square. That's the intensity formula. This alpha was equal to, if I can look it up, is it's really not that important for the pattern, but I think it's maybe like a half c epsilon naught or something like that. All right, but I'm not clear on, I'm just calling from memory. Okay, so we have E sub p, and this is time average this quantity, right? Well, so I have a AP square and time average of cosine square k r average minus omega t, time average. Well, this just oscillating up and down. What's the time average of that? Of course, just oscillation itself time average is 0. When you square it, the time average is half. So I can absorb that in alpha. So it's like a beta AP square. So let's absorb everything beta in 2E0. So beta, I'll just carry it alpha over 2. I change my mind. Times 4 E0 square. So these are all constant, some large volume. Then there's cosine square, R1 minus R2 k over 2. Now these change as you here's the P, and this is R1 and this is R2, and if I go to another point P, this will be R1 and this will be R2. They will change, R1, R2. So this will depend on where the P is located. So this intensity says it's going to vary on the screen, and in a very nice way. So let's look at a little bit closely. So some kind of, I'm going to call it A max. Let's call it intensity max, and then have a cosine square. If I write k equals to 2 pi over lambda, I get 2 cancels out, pi times delta r, the difference between the two, and we can just say absolute value here over 2. So you can say whenever this is going to go between 1 and 0, right? This varies between 1 and 0. So I have a 0 and 1, and when delta is 0, it's maximum. It's like that. So at some values of delta r is going to be 0, and some value of delta r is going to be 1. And so we can figure out what the conditions will be. So when do you think is going to be 0, 1? Well, we should be able to see it by using half angle formula. So if I do it times 2 of this stuff, and that's 2 of cosine square is 1 plus cosine 2 theta, 2 pi, this is lambda, 2 pi delta r over lambda. So it's actually telling me when this is equal to minus 1 is going to be 0. So cosine 2 pi delta r over lambda equal to 1 That's where the max is. If if uh, if 2 pi delta r over lambda is n times 2 pi, all evens, right? So for n equal to 0, plus or minus 1, plus or minus 2, etc. So these are places where the maximum will occur. This is when the max is max intensity. When it's minus 1, if I have 2 pi delta r over lambda is actually m times pi, but m only odd, right? So m only odd. So m can be plus or minus 1, plus or minus 2, plus minus 3, plus or minus 5, etc. So if we look more closely here, delta r has to be, we're not talking about absolute delta r, is pi cancelled out, m lambda over 2. So this is a destructive interference condition, destructive interference condition. Let's work this guy out for constructive. So when I look at delta r over here is delta r is over here is going to be 2 pi cancels out n times lambda, and n can be 0, plus or minus 1, plus or minus 2, plus or minus 3, etc. So these are constructive interference conditions in this situation. Maybe you've seen this in earlier class. However, this working with R's is a little bit inconvenient, and it'll be nice to know if we can write those in terms of this angle to P. If we can write this with this angle theta, okay, and some of the angle theta, and how far apart these guys are. So if these guys are apart, d apart, then can we write r1 minus r2 in terms of this? And it turns out yes, under certain conditions, right? So we have a geometry like this, P is here, and you have here, and so the P is here, okay? So imagine, say this R1 is small, it's smaller than R2. So I take a arc, I take a circle of radius so this is radius r. So we are looking for this distance, that's the delta r. All right, so if I know this distance as d, and if this is very far, r1 r2 much greater than d, then you can draw a tangent here. Let's draw a tangent to this circle. Oh, I had to draw it over here. Then this where it crosses delta r is going to be almost equal to delta r. So this is an approximate delta r. And if this is the angle theta we look in, so that's this angle to the point theta is almost that theta. You can say this is theta, then in this 90-degree thing, this is 90 minus theta, 90 degrees minus theta. Then this angle up here in the corner is theta. So we have a right angle triangle. This is 90 degrees and this is theta, and this is almost delta r, and this is d. So delta r is simply d sine theta. Actually, this is the overkill. It's almost d theta. So what we have over here, this we can write these conditions by d theta, theta in radian. You want to be more precise, you may want to say d sine theta. I don't know why would you say d sine theta, because you made all kinds of linear approximation here, very far away, theta is small, right? So this, we already said theta is small, but for some reason that traditionally we actually use d sine theta instead of d theta here. So we can say this is d theta, or you can say d sine theta. It's up to you. They're all going to be very close to each other when this approximation is correct. So we got an alternative way of writing our conditions. So d sine theta equals to, we can just write a single one, m lambda over 2. So we are going, if I have m is 0 plus or minus 2 plus or minus 4 plus or minus 6, this will capture constructive. And when m equals to plus or minus 1 plus or minus 2 plus or minus 3, this is going to capture destructive. And we might say, just for sake of completeness, delta r between the two paths is this. Okay, so I'm going to stop here. This is an introduction to interference of 2-point sources. What I want to talk to you later is about how things can go wrong. When will I not see it? I didn't get to talk about this idea of coherence. Mathematically looks like everything's hunky-dory, very nice, it's gonna always work out. But you can see I use this thing called same frequency. I use this called sync with each other, Well, what if they go out of sync from each other? What if they have more higher frequency? You can also say if even I started with a sync, but the wave coming here from here, wave 1 versus wave 2, they're not coming at the same time. They come at a different time, right? But I assume they're coming at the same time. I use the same time for both of them, right? I use the same time for A and B. I use the same time for A and B. So what happens if some of those assumptions don't work out? So we will talk about next this very, very important thing, that you don't see interference pattern just because you say you have a flashlight here and another flashlight here. Why don't you see an interference pattern? it turns out that it gets washed away because of lack of coherence. So this coherence is a very fundamental requirement for you to see the interference pattern. So that's the one I'm going to do next. But I'm going to stop the video here. I'll see you in another time. Bye.